And then I'll just leave the word to Michal. Yeah, it will also be added to the program homepage.
Okay, so thanks everyone for coming. Thanks for the invitation. So I would like to tell you about something about our results, and this is called lower bounds for elimination via regularity or weak regularity. And this is actually joint work with Arkadev, Chatopadai, Pavel Dvořák, my student, Bruno Lev, and Shagnik Mutkopadai, who was a student of Arkadev at the time. So what is this about actually? So this is in the context of actually what sometimes people actually call direct sum questions, and in particular direct sum questions in communication. So we will have a communication problem. We will have some function f, and we have Alice and Bob, and Alice is going to get like k strings, x1 up to xk, and Bob is going to get also k strings, y1 up to yk. And these strings are actually from domain 0, 1 to the n. And there is some function, actually, f, which is basically the usual function. So it's actually from domain 0, 1 to the n, and 0, 1 to the n into, say, 0, 1. So it's, this is standard. But the difference is that we actually do have, instead of actually having like one instance of the problem, Alice and Bob actually somehow should solve this f on all pairs of these instances. Not on all pairs, but actually on like on x1, y1, x2, y2, etc. So you just pair them like this. So so there are actually multiple questions actually related to this problem, and so one kind of the ultimate one is you just want to output everything. So you want to actually output f of x1, y1, f of x2, y2, etc. up to f of xk, yk. And the question is, how much communication does this need? And does it actually, do you need actually k times as much communication as if you just have single f? That's basically the question. And this has a relation to circuit lower bounds, and it was actually introduced like a long time back, and Ras, Karchmar, and Wiedersen actually looked at it. And there are actually some examples where actually you can save, and there are some partial results on this. So this is actually, this is not what we are going to be interested in. We are actually going to be interested in actually somehow weakening of this problem. And that's actually the following type of weakening. So let's say it's a problem which is called elimination, and I will actually try to tell you where it comes from originally. But it's much weaker actually question. So you get again like these instances x1 up to xk and y1 up to yk. And your goal is to output some string z, which is actually not equal to f of x1, y1 up to f of xk, yk. So you basically want to output some string which actually differs from one of these function values. And so that's elimination. So this problem actually was studied in complexity theory actually for problems like in basically structural complexity, like for problems like SAT. So you get like several SAT instances, and you should that means you get several formulas, and you should actually point out to one which actually say is not satisfiable, or which one is satisfiable. And people study this a lot in 80s. And you can see that this problem is actually much easier than the direct sum question, because you don't need to solve all the instances. Easy way to solve this problem is to solve the first instance, and if it's actually you get a solution, and then you just basically flip the answer, and that gives you a valid output for elimination. So elimination is actually not a function; it's actually a relation. So you can actually output anything which fits this requirement. And then there are actually some other actually either weakening or strengthening of this problem. So one of them is actually so-called choose problem, where what you can do is actually Alice and Bob can kind of pick whatever instance they want to solve, and they solve that instance. So they can actually they can pick basically some I and output I f xi yi. And there is another one which actually people look at, and that's actually called agreement. And in the agreement case, what you are promised is that either all instances are actually negative or all are positive, and you should just distinguish which one is the case. And if you get some mixed input, then it doesn't matter what you output. So basically, the requirement is only on consistent inputs. So you should output basically answer whether all fi or f xi yi are equal f xj yj. So whether all of them are equal, and if yes, whether they are 1 or not. So you basically should answer, but you should basically check whether all this is equal 1. So you can see that these programs actually have various complexities, and the question is, if I give you actually several instances like this, whether you can actually do something better than actually picking one of the instances and solve it. So that's the question we are actually looking at. And if you look on what the problems on these problems, it's clear that actually some problems are easier than others. So, for example, if you can solve efficiently choose, then you can solve efficiently elimination, because if you run protocol for choose, then you get basically output I f x I y I, and then you can just actually negate that output and output some fill in the rest. So one thing to realize, so what we will be actually interested in, we will be interested in a probabilistic protocol. So we will be interested in probabilistic communication complexity. So we will actually allow error. And if you actually allow randomized computation, then it's clear that actually the error, you should actually put some requirement on the error. So you'll use actually randomized communication. So you want to, so we will use randomized communication. And if I allow you to use randomized communication, then of course there is a trivial protocol. You basically just don't look on anything, and you just output a random string. And under that actually model, if you, it's easy to basically be correct. Such a trivial protocol is going to be correct with probability basically 1 minus 2 to the minus k. So such a protocol basically is trivial. So you should basically, so you should basically require, for this to be interesting, you should require that the error is actually much less than 2 to the minus k. Or maybe not much less, but it should be better 2 to the minus k, otherwise it's trivial.
So are you thinking elimination is a problem?
Say it again?
So this is for
right, sorry. Now I'm thinking of elimination. Okay, so from now on I'm actually going to focus on elimination. So since actually elimination is harder than either this problem or this problem, because we can reduce it to either of these, our goal will be actually to prove lower bounds for elimination. So that means that if we prove it for elimination, then we will actually get also lower bounds for choose and agreement. So our goal will be to actually show that basically these problems for large class of functions, you basically have to actually solve at least one of the instances. Essentially, that's kind of the goal of the talk. So we need actually a really small error, and otherwise the problem is trivial. And then the question is, what can you do? One thing actually, so we don't necessarily have to actually require that actually both parties learn the output, because the output, if the k is actually large, then just communicating the output could be actually expensive. Although we will actually consider like public coin protocols, so then it could actually, it may not be public coin protocols. So if we consider public coin, and actually the protocol which I said, actually both parties would learn the output, because they would actually use the same random bits to actually solve the problem. So can you actually do anything better in this protocol, in this model? And it turns out that actually you can. Sorry. And you you can do actually slightly better than actually just actually solving one of the instances, and you can solve at least a tiny bit. And that's actually going to be in the case when actually one party will lend the output. So we say we kind of relax the requirement that all parties actually lend the output, and then we can do slightly better. In particular, if you take any function f on n-bit outputs, and you take k, which is not too big, say less than n, then we can solve this elimination of f to the k, so elimination for this function f, using n minus half log k bits. So this is actually slightly better than just actually the trivial upper bound, which would be actually n bit. So that's what we can do. And the error is going to be, as required, is going to be less than 2 to the minus k. So what's the protocol? So this protocol is actually from a paper by Biemel, Weinrep, and 2 other people. Biemel, Weinrep. Say that again? No. Okay, and 2 others. And so let me actually explain you how the protocol works. So you can actually do a little bit. So here is what you can do. So let's actually the Alice and Bob will actually share some random strings r1, r2, etc. of length n. And here is how they proceed. So actually Alice looks on her instances and checks whether actually she got enough different instances. So if all the instances would be the same, then they will do something else. But if she got actually at least square root of k distinct inputs, then what she's going to do is actually she's going to look into these r1, r2, etc. And she's actually going to check whether one of her inputs actually appear in that list. So she is actually going to use this randomness as basically a list of instances. So she will actually look for the first j, which actually corresponds to first j among these strings, rj, which corresponds to one of her inputs. And if she finds such an input, then she actually sends this index j to Bob. And what Bob does, then Bob actually computes basically f of rj x1, sorry, it should be actually the other way around, and rj x2, rj xk, and just outputs negation for each of these. So you can see that actually, since rj was actually, oh, actually, sorry, this should be y. Sorry. So you can see that actually, since actually rj was one of the strings of ls, actually they are going to output a valid output for the elimination problem. And how much do they communicate? Well, they need to communicate basically n minus half log k bits actually in this setup. So in this setup, basically they output correctly if there is such j. If there is no such j, they just actually flip random bits and they output random bits. So if there is some chance that actually none of the rj's actually matches input of ls, and then they are out of luck, and then they just output randomly. Now the situation could be reversed. So actually Bob could have a lot of different instances. If that's the case, then they just do the same, but they just reverse Alice and Bob. So it's the same scenario. So the last remaining case is actually if actually none of them has actually a lot of different instances. But if that happens, then that means that they have a lot of basically instances the same. So in particular, Alice has square root of k instances which are all the same. And then, but then actually also Bob has like but if you look on those instances, since actually Bob has also more than actually fewer than square root of k instances, actually there is going to be actually a pair of instances over here, some L and L prime, which are exactly the same. So what actually what Alice is going to do? She is actually going to send over. The list of the indices, which she picks the largest, the string which actually appears the most number of times. She sends over the indices, and then actually Bob just looks for a pair L and L prime, which is actually also the same. They solve. He solves and he doesn't actually solve anything. He just outputs for one of the strings, one of the output he outputs 0, and for other pair he actually outputs 1. And he knows that this is actually going to be one of them is inconsistent with the output. So in this case, basically the amounts of communication is like k log n bits, or actually square root of k log n bits roughly. So it also actually fits this communication budget. And what's the error? Well, the error actually comes only in the case if actually Alice is not able to find the index j, which would correspond to one of her strings. So basically, the string, none of her strings actually appear in this list. But that has actually constant probability of occurring. So with constant probability, they actually solve it correctly. With non-constant, they actually solve it, so they actually get some small advantage actually over this trivial 2 to the minus k situation. So they actually they have error smaller than 2 to the k. So this shows that actually you can actually do something non-trivial for this problem. And the question is actually how far you can actually push this. So what we show is that you cannot actually push it too much. So one of our main results actually is that we basically prove the following theorem. So, which is like our main technical tool. So what we are going to show is that. So maybe let me just state what we prove, and then let me explain why is it what we need. So let's take some mu, which is distribution on string 0, 1 to the n. And let's say we take k, which is actually smaller than 1 over 64 times discrepancy with respect to mu of the function f. And I will explain in a second what I mean by this. Then the distributional deterministic complexity with respect to the measure mu to the k of the problem elimination composed of this f of k. So this must be at least logarithm of 1 over discrepancy with respect to measure f, measure mu of f, minus k plus some small error term log 1 minus epsilon times 2 to the minus k plus some constant. So this is our main technical result, and let me actually try to explain you the meaning of this, or what's a corollary. So what this says is basically, so there is by Gauss principle actually there is a duality between actually performance on a distribution of deterministic protocols and randomized communication complexity. So in particular, actually randomized communication complexity actually corresponds to picking the worst case measure, worst case distribution on string 0, 1 and building for it a deterministic protocol. And what we are saying is that whatever distribution you take, the deterministic complexity, the distributional with error epsilon, so that means like if you allow error, but the error is measured with respect to the pairs of inputs, and the error should be at most epsilon, so the deterministic protocol should be mostly correct, except for a fraction epsilon of inputs. Then the elimination of composed of fk is at least logarithm of 1 over discrepancy of f with respect to this measure minus log k, minus some small quantities. So what this means is that if you have function which actually has a very small discrepancy and you have some distribution on which it has small discrepancy, then you basically get a good lower bound. And this is actually, there are actually functions for which we have that. So that's actually, for example, for inner product. So for inner product, what this implies is that if we take inner product, then the randomized complexity of elimination.
Question?
Yeah.
Maybe I'm missing something simple. What's the definition of discrepancy for a relation?
So this is actually for the original function f. So it's
The left hand side.
oh, this is not
That's not discrepancy. My bad. Sorry. I apologize.
Okay. So. So it implies, for example, that the randomized complexity of elimination of the inner product, so if actually they are trying to solve inner product of these instances, is at least basically n½ minus log k minus this minus these small order terms. Sorry, plus. So basically what it says is that, for example, for inner product, basically the best you can do is basically pick one of the instances and solve it, as long as k is not too big.
So this is really n in the previous set, or is
No, this is n over 2.
so?
N over 2.
But your upper bound was.
So this doesn't contradict the upper bound because the upper bound.
But it's off by n over 2.
Well, there is actually factor 2 which we are losing, right?
So is there any other function for which we know discrepancy lower bounds of greater than n over 2?
That's a good question.
Corresponding thing.
You mean the corresponding complexity, right? So, for example, a greater than function. So you get two strings, and you should they represent integers, and you should actually decide which one is actually bigger. So, for greater than, there is a distribution by Braverman and Weinstein, which actually has discrepancy like 1 over square root of n. So you get basically like half log n minus log k plus again this. Okay, so this is some of the conclusions. So basically, there are actually many functions for which we actually know a relationship between actually discrepancy and their communication complexity. It's basically tight. So for those functions, actually, we do get pretty much tight results. So how do we actually prove this, or how does this come? Where does it come from? So it actually comes from so this bound actually comes from these bounds come from actually looking at what the error actually means, and let me actually try to define what regularity is and how does it actually relate to the error. So where do we actually if I have a communication protocol for f, where does the error actually comes from? So let's say I have some deterministic protocol. So let me actually look on deterministic protocol, and again I assume that there is some fixed distribution mu on the inputs. And I'm looking on deterministic protocols which actually make error on some inputs and are correct elsewhere. So I have deterministic communication protocol which say communicates C bits of communication. So now if I look on the, and this is actually for my original function f. So this is not for elimination, but I have, sorry, no, this is for elimination. Okay, so actually I do consider actually some measure mu, so it's actually on k. So where does the error actually? How does the error actually come from? So this is all the usual matrix of the function of whatever the protocol computes. So it has inputs 0, 1 to the kn, and 0, 1 to the kn. And well, the deterministic protocol actually splits, as usually, the matrix into rectangles. And so we look on these rectangles. And now, how does actually inside of let's look on inside of each rectangle. So we have there actually various possible k-tuples of inputs, and each k-tuple actually, if we would just actually evaluate the function on all the corresponding pairs, then it actually gives you various answers. So I'm going to split this rectangle based on z, where z is basically the output of all the functions. So x1, y1. So z is equal to f x1, y1, f x2, y2, etc. up to xk, yk. So I can split it according to the output value. According to the output value. Now, what is actually error in this case? So the error in this case is because if you are outputting some z, if my protocol is outputting some z, so it's a deterministic protocol, it should output basically k bits. And if it outputs some z, then what is going to be error in this case? That's going to be exactly the inputs which actually, if this rectangle is outputting z, so then the error are all the inputs which actually give you z. So that's like this part r sub z, where r sub z are exactly the inputs which actually map to z if you evaluate this function. So this whole thing is a rectangle. I have like there are some large rectangles because I have c bits of communication. Then this is basically the error. And if you actually sum this error over all the rectangles, then that gives you the total error of the protocol. So how does it actually? So what we can actually show is that we can actually relate this total error actually to discrepancy. And let me actually just in a few remaining minutes actually explain you how that actually works. So what we have here is we have here this rectangle, and like imagine that actually, so there are two possible scenarios. So maybe if there is actually some value missing in this rectangle, then there would be zero error. Now the worst case for us is actually if for each z, basically all the rectangles are about the same size. So I have here like 2 to the k different, sorry, it's not the rectangle, but these parts which r is actually partitioned into. So the problem for us, the error will be large if actually all the parts corresponding to various z's will be about the same size. So with respect to the measure mu, so the problem is actually if for all z, the rectangle rz, or the part of rectangle r corresponding to z, if this is going to be roughly 2 to the minus k of the total measure mu r of the rectangle. Then, so if all the guys basically will be about the same size, then that guarantees you that you are actually going to make an error on that rectangle. And it basically guarantees you that if you sum over everything, then you will basically end up exactly with the error you are looking for. So it would give you error which is roughly 2 to the minus k. So the question is actually for which functions actually you can show that if whenever you take a rectangle, it's actually going to be balanced, balancedly split actually into various outputs. And it turns out that this is actually this is closely related to the discrepancy of the original function f. And since I don't have much time, I cannot tell you. But if let me just say that so we call this actually property which is called regularity. So if actually it is true that for every rectangle whenever you actually split it into these pieces RZ, then all of them are about the same size, then we call that regularity. And this is actually a property which was used, and it's actually used heavily nowadays in the lifting, in communication complexity for lifting. And it basically, you can show that if a function has low discrepancy, then it's actually going to be regular. And that's kind of the bottom line of the proof. So that's and once it's regular, then actually you can argue that it requires actually a lot of communication. So I guess since I'm out of time, maybe perhaps let me stop here.
So does discrepancy look like the right bound for here, or could it be something much larger?
Right. So we actually don't know. So we don't have an example where we could actually prove distinction between discrepancy and communication. I mean, we would actually guess that the right bound is actually that the randomized communication complexity is the communication complexity of single instance, but we cannot prove it.
What happens if you're talking about a relation in the beginning? What if F was a relation in the beginning?
Oh, if F was a relation at the beginning. Yeah, I don't know actually. That's a good question.
So there are no functions for which the upper bound is close to this lower bound?
You mean because of this factor and half, and then? No, we don't know any actually. So it would be actually interesting to basically like either kind of close these gaps or actually find a better upper bounds actually. So this is like very, very, very simple upper bound. So maybe you can actually do something better.
We know the discrepancy corresponds to some weird model of communication. So maybe for this model, this is actually tight.
Right. What would be actually really interesting is actually to get rid of this log k. So basically there is this log k basically means that like once you have too many instances, then this lower bound doesn't tell you anything. So for example, for elimination of greater than, you basically don't get anything once k is like say linear in n, but say for square root of n you still get something non-trivial. For inner product, you basically get something non-trivial up to basically exponential k. But it's actually interesting whether it would be interesting to know what happens actually if you go with k beyond actually exponential. So it's not clear at all actually. And
You can't, right? Because of the upper bound.
Say it again.
N minus half log k.
But
So the log k is needed.
But if OK at most 10.
That's for small k.
right, but this works only for small k actually.
Oh.
More questions? Otherwise, let's thank Michal again.